Myself, I'm Keshan from CSC Secondary. My topic is on the minimum mean square solution for the discrete time difference equations with random terminals distributed by multiplicative noise. Introduction. The continuous time backward stochastic differential equation were first introduced by Bismuth for linear case to study a sort of stochastic optimal problems whose terminal values are usually equipped with random variables and the solutions are required to be adapted to a given filtration. Since Paradox and Peng proved the existence and inequalences of the solutions of nonlinear BSDs, the series of BSDs have been developed rapidly, including BSDs forward, backward, stochastic differential equations, G expectation, etc., and also have been applied to the study of economic and financial theory. Next, in order to obtain the numeric solutions of BSDE, Gobet, etc., propose a numerical scheme based on iterative regressions on function basis, which coefficients are evaluated using Monte Carlo simulations. Since Paradox and Peng proved the existence and inequalences of the solutions of nonlinear BSDs, the theories of BSDs have been developed rapidly, including BSDs forward, backward, stochastic differential equation G expectations, etc., and also have been applied to the study of economic and financial theory. In order to obtain the numeric solutions of BSDs, Gobet, etc., propose a numerical scheme based on iterative regressions on function basis, which coefficients are evaluated using Monte Carlo simulations. By giving a simulation based estimator of the conditional expectation operator, suggest a discrete time approximation for decoupled forward backward stochastic differential equations. Those show that discrete time systems are easier to simulate and devise than continuous time systems. So many models are based on discrete time difference equations. In this paper, motivated by the continuous time backward stochastic differential equations proposed by Paradox R and Peng, we present the discrete time stochastic difference equation with multiplicative noise as the following form. By giving a simulation based estimator of the conditional expectation operator, suggest a discrete time approximation for decoupled forward backward stochastic differential equations. Those show that discrete time systems are easier to simulate and devise than continuous time systems. So many models are based on discrete time difference equations. In this paper, motivated by the continuous time backward stochastic differential equations proposed by Paradox and Peng, we present the discrete time stochastic difference equation with multiplicative noise as the following form: yk equals to fk of yk plus 1 zk, n equals to -1. Suppose is a complete probability space and be a sequence of a measurable or valued random variables. Let f of k belongs to f be the sigma fields generated by w0 w1 up to 7 wk minus 1 example, and f0 is the trivial field example. It's easy to see that f of k minus 1 belongs to f of k. Denote f the sequence of sigma fields, which is also called filtration, for a random sequence y equals to yk. If for every k equals to 0, 1 and yk is fk measurable, then we call that y is an f adapted sequence of process. Denote L square, the set of all Rn valued measurable random variables and its element x satisfies. We also denote We assume that WK satisfies the following conditions. Now we suppose WK equals to 0 in BSDE is given random sequence satisfying to and FK R power n into R power n into D belongs to R power n is measurable. We also suppose the following conditions hold. For every y belongs to R power n, z belongs to R power n into D, Fk of y comma z is Fk measurable and Fk of 0 comma 0 belongs to L square. There exists a constant C1 greater than 0 and C2 belongs to 0 comma 1 by root D such that k equals to 0 n minus 1. Suppose Fk into R power n into R power n into D satisfies 3, then for every yk plus 1 there exists a unique zk belongs to L square such that zk equals to E of Fk of yk plus 1 comma zk wk f of k. Proof: construct a map T on L square f of k R power n into D. By the fixed point theorem, there exists a unique zk belongs to L square satisfying 4. This ends the proof. The following example shows that the BSDE does not necessarily have the f adapted solutions yk zk belongs to h of k in the usual sense. In order to estimate such dilemmas, we introduce the definition of MMS solutions for BSD. For each n belongs to L square, we define the mean square functions gk as following. Suppose 2 and 3 hold, then for every the backward stochastic difference equations one have a unique MMS solution. Now we review example 3.1 equals to we see that is the one step MMS solution of BSD according to various situations and the researching background. There are many BSDs with different forms. In the following we discuss some backward stochastic difference equations with multiplicative noises. Consider the backward stochastic difference equations with following them. Similar to the proof of theorem 3.1, we can prove the following results. Suppose gk and hk satisfy equation 7, then there exists a unique adapted MMS solution. Yk, zk belongs to h of k to BSD. Moreover, the solutions yk, zk are solved with the following forms. For the following types of backward stochastic difference equations corresponding to the degraded form of the continuous cases, see equation 3 in equation 7 for detail, where wk is independent and identically normal distributed with, and if n is large enough, it's easy to see that is the MMS solution of equation 9. This solution is just the results given by equation 7 and 8. Consider the following optimal control problem discussed in minimize the cost. By proposition 3.1, we can see the BSD's equation 12 have a unique adapted MMS solution, and the theorem 3.1 of 12 we can obtain the maximum principle for the optimal control problem. Consider the following backward stochastic difference equation distributed by multiplicative noises, where E0, E1, E1 En are independent identically distributed Bernoulli sequences with P of E, k equals to minus 1 equals to P of E, k equals to 1 equals to 1 by 2. The continuous time backward stochastic differential equations BSDs were first introduced by Bismuth for linear case to study a sort of stochastic optimal problems whose terminal values are usually equipped with random variables and the solutions are required to be adapted to a given filtration. Since Pardox and Peng proved the existence of inequalities of the solutions of a nonlinear BSDs. The theories of a BSDs have been developed rapidly, including BSDs, forward, backward, stochastic differential equations, G expectation, etc., and also have been applied to the study of economic and financial theory. In order to obtain the numeric solutions of a BSDs, Gobet, etc., propose a numerical scheme based on iterative regressions on a function basis, which coefficients are evaluated using Monte Carlo simulations. By giving a simulation based estimator of the conditional expectation operator, Tausig suggested discrete time approximation for decoupled forward-backward stochastic differential equations. Those show that discrete time systems are easier to simulate and devise them continuous time systems. So many models are based on the discrete time difference equations. In this paper, motivated by the continuous time backward stochastic differential equation proposed by Paradox and Payne, we present the discrete time stochastic difference equation with the multiplicative noise as the following form. Suppose is a complete probability space and be sequence measurable valued random variables. Let be the sigma fields generated by W1 up to 7 Wk equals to 1. Example, and if not is trivial sigma field, it's easy to see that to note if the sequence of sigma fields, which is also called filtration for a random sequence. If for every k equals to 0, 1 measurable, then we call that y is an f adapted sequence of process. Denote L square the set of all r power n valued f of k measurable random variables and its element x satisfies. We also donate. We assume that satisfies the following conditions. We have obtained the existence and uniqueness of the solutions of the kind of backward stochastic difference equations with random terminals under the meaning of MMS solution, where the BSDs are distributed by multiplicative noises. Thank you.